Hello everybody, this is Supplemental, and we are going to be going through the Cert 3 in Electrotechnology, as well as the Cert 2 in Electrotechnology at some point in the future. And to start us off, we're going to be introducing AC theory. Now, in order to effectively teach AC theory, we're going to have a quick recap of what DC theory you should remember from earlier on in your apprenticeship. Okay, here are the key objectives for this episode. We're going to recall what voltage, current, resistance, and capacitance are in DC circuits. We're going to go through basic series and parallel circuits involving capacitors and resistors. And we're also going to just complete some revision questions throughout the episode. A quick note, and I'm sure everyone's aware of this if you're doing an apprenticeship right now, but if you want, DC theory is actually now called solve problem in single and multiple part circuits, and the actual qualification that we're all doing has changed from 3811 to 3820. Let's start us off with voltage. Recall that voltage is just a potential difference that enables the movement of electrons in a conductive medium. As an electrician, our conductive medium is typically going to be a conductor, a cable. So, we have two types of voltage that we need to be aware of, AC and DC. Now, up to this point, you've probably seen what DC voltage actually looks like. It's just a straight line represented by the red here on screen. This is a graph of what happens when the voltage, V, is equal to 50. A 50 volt DC supply will have a constant voltage. The voltage doesn't actually change. However, if you look at an AC voltage, let's say in this case, the maximum voltage for this would be 100 volts. What you see is that the voltage is actually not a straight line. It's a wave. And we'll deal more with what this wave entails and what the consequences of having a wave, a sine wave, are for AC supplies. But just be aware for now that AC sine waves and DC voltage, AC voltage and DC voltage have different properties because of this here. Let's talk about current. So current is what happens when you have a potential difference in a circuit and you have a completely closed circuit with a conductive medium. So you've roughed in a house and you've introduced a supply, and if all the protective devices are closed and all the switches are closed making contact, what will happen is that potential difference will enable electrons to move through from the supply into the load, whether it's a TV or an oven or an air conditioner, and then back to the supply. Okay, we measure it in amps. And it's important to note that in DC theory, we got introduced to two types of current flow. Conventional current flow, shown on screen, and electron current flow. With conventional current flow, this was used more so when they were discovering and still studying electricity. And electricity is still being studied now. But when they first studied it, they believed that you had current moving from the positive terminal of a supply through the switch to the load back to the supply's negative terminal. But what we know now is that electrons are what are largely responsible for current flow, and electrons are negatively charged. So what actually would happen is they would move out of the negative terminal through your protected devices and switches, through your load, and then to the positive terminal, right? Electrons are negatively charged. So either form is acceptable for drawing circuit diagrams in DC theory. It's just important to know what the difference between them is. Also note that I haven't drawn with the correct notation. So you'd have to draw one side as red to the load and the other return path as black, right? I haven't done that. So this would, going through the switch to the supply would have to be in red, and then out of the load back to the supply would be in black. So this should be red and this should be black, but I've just drawn both as black. So just excuse that. Okay, talking about having a complete circuit, it's important to remember from DC theory that there's 4 general states that your circuit can exist in. Your circuit can be closed and everything's working fine. You have all your protective devices and your switch is closed. And that means that you can have electrons moving as well as a potential difference, allowing electrons to move from the supply through to your TV or whatever load that you have, and then back to the supply. That's a closed circuit, everything's fine. You can have an open circuit where your switch or your protective devices are open. That means that electrons can't actually move, even if there is a potential difference. There isn't a complete circuit there. But there's two other forms that your circuit can exist in, right? And they relate to having overcurrent, too much current or more current than the particular circuit is designed to handle. So we can talk about short circuit and overloaded circuits. If you have a short circuit, all that's happened is that you've provided your current a pathway to bypass the load. Okay? The load has a certain resistance that controls the amount of current that flows. It's been designed for that. If you introduce a short circuit where your current can bypass that load and go back to the supply, what happens is that you're going to have unsafe levels of current flowing very, very quickly. And then the overloaded circuit is simply when you have more loads connected than your circuit's been designed for. Okay, so your circuit might be designed to handle 10 socket outlets, let's say, and people are plugging in different appliances into that socket outlet, and that's fine. But let's say they plug in very heavy current demanding appliances into those 10 amp socket outlets. What's going to happen over time is that circuit is going to be drawing more than it's actually designed for. The cable will heat up over a long period of time. You won't notice it immediately. And then ultimately the cable will get too hot and your circuit breaker or your RCBO will trip because it's sensed that the cable's gotten too hot. So if we look at it from the AS3000, the two situations that I'm describing are from clause 1.4.42 and 1.4.43. And there's more clauses that you can look into that help define what we're discussing, but we'll deal with that in future episodes. Okay, so we've talked about voltage. We've had a quick recap about current. Let's talk about resistance, which was introduced in DC theory. So resistance is just opposition to current flow. And the thing I want to discuss is this image here that links all the different variables that make resistance what it is. It's telling us that resistance is related to the resistivity of a material, an innate property, right? So an insulator like wood or something else that isn't very conductive is going to have quite a large resistivity. It's not going to really allow current to flow. Whereas something like copper and aluminium, they're going to have a much, much smaller resistivity. So resistivity, right, is a property that you really can't change. The material is either really good at conducting or it really doesn't like conducting electrons or current. Another thing that impacts resistance, okay, is the length of your circuit. And we'll talk about this in AC theory. You'll talk about it again in cable selection. You talk about it in maximum demand. You'll talk about it in earth fault loop impedance. Length has a lot to play with it, and something that we can actually control. We can't really control resistivity. We can choose copper. We can choose aluminium. We really can't do much else. But we can control the length of our circuits quite well. So what this tells us is that if the resistance is directly proportional to the length, then if you increase the length of your conductor, your resistance is going to increase the same amount. If you double your length, you're going to, all other things being equal, you're going to double your resistance. So resistivity and length are directly proportional to resistance. You really can't control resistivity. You can control your length somewhat. If a motor has to be 100 meters away, because that's where, the conveyor belt starts or whatever, you really don't have too much play with that. The last factor we're going to discuss with resistance is the area, the surface, the cross-sectional area of your conductor, and that is something that we can definitely control. Just upsize and cable. What this tells us is that the resistance actually has an inverse relationship with cross-sectional area. If you double the size of your cable from 2.5 to 4 mil. Oh, sorry, that's not double, but let's say you just go to 4 mil or 6 mil or 10 mil, whatever it is. What's actually going to happen is your resistance will decrease. So to recap, this equation here below is what links resistivity, length, cross-sectional area, those three factors, and resistance, this resistor here. And it's important to remember that certain things we can't control and other factors we have quite a lot of control over. Let's quickly go through Ohm's law before jumping into a couple of examples for series and parallel circuits. Recall that Ohm's law is V equals IR, and although I'm not the way your teachers might have told you to learn Ohm's law, to think of it as a triangle, VIR. I thought that this image from Wikipedia was actually pretty cool. So if you just put your hand over a certain variable that you're trying to find, in this case, you're trying to find voltage, put your hand over it, it leaves you with IR. So that means that voltage is equal to current times resistance. And you can do the same for current. You block off current, you're going to have voltage divided by resistance. If you block off resistance, you're left with voltage divided by current. So just recall that Ohm's law is quite an important formula to know, and how you use it is also important. And off to the right there, I've just left the power formulas, which are also important to know. We're going to go through power factor. We're going to go through the different types of power that you actually have in AC circuits. So it's important to remember that these equations apply for purely resistive circuits. And then when you introduce things like capacitors and inductors, they start to differ a little bit. Okay, so now we're going to have an attempt at this series circuit that you see on screen. Let's start with the first question. I encourage you to pause the video, have an attempt, then have a look at the solutions. The first question that we have to do is, what is the total resistance? Question 1, what is the total resistance? And you can see up here that in a series circuit, the total resistance is just equal to the sum of all resistances. So what we're going to do is we're going to add resistor 1, which is 2500 ohms. Remember, 2500 ohms is the same as 2.5 kilo ohms, plus resistor 2, which is 1500 ohms, and that's going to give us 4000 ohms. That's the first question, okay? Now, the next question is, what's the current value flowing through both through the ammeters? Ignore the word both. There's only one ammeter in this currently. Ignore the word both. Only one ammeter, but if there was a second one, it'd be here. Okay, so how do we work that out? Well, question 2. Remember that in a series circuit, the value of current flowing through at the beginning of the circuit is the same as the value of current flowing through at the end of the circuit. There's only one pathway that the current can take. So that means the value of the current actually doesn't change. So in order to work out the total current, we need to use Ohm's law, which isn't currently on screen, but I'll write it down to remind us. Remember that Ohm's law states that V equals I R, and you can transpose that and say that current total is going to be the voltage of the supply, or the total voltage, divided by the total resistance. The voltage of supply is 90 volts. The total current, the total resistance we've worked out to be 4000 ohms. Let's bring up the calculator. 90 divided by 4000, 0.0225. .0225 amps. That's the total current flowing. Now, importantly, guys, this circuit that we've drawn here, you have to realize that it actually simplifies to this. So then we can find an equivalent resistance. There's our ammeter. There's our closed switch. There's our 90 volt supply. Not the best at drawing just yet. I will get better. So that's actually what we've simplified it to. We still have a voltmeter here. right? This resistance is no longer just 2.5, 1.5. It's now just 4 kilo ohms, or 4,000 ohms. You got to realize that we've simplified that to this, and we're saying what's the value of current flowing through this resistor and back to the supply. There's 0.0225 amps flowing through this resistor. The next question is what's the voltage drop over resistor 1? So we're going to have to go between both of these because we can work out what it doesn't say it, but let's bypass that question temporarily. We're still going to do question 3, but let's add something to it. Let's work out what the total voltage drop would be over this 4,000 ohm resistor, and then we'll work out what the voltage drop over these two resistors would be. So remember, Ohm's law tells us that V equals IR. So then what we can say is that the voltage drop here would be the total current multiplied by the total resistance. So we've conveniently worked out the resistance total as 4,000 and the current total as 0.025. So what that tells us is that we can just go VD is going to be 0.0225 amps times 4,000 ohms. The total voltage drop in this case would be, bring up the calculator. We've got 0.0225 times 4,000 ohms. That is 90 volts, which makes sense. 90 volts. If we just have a 4,000 ohm resistor, you're going to have all of the voltage dropped off on one resistor. That makes sense. But what we've been shown is we have two resistors. So let's work out how much volts are dropping over resistor 1. So I'm going to then say question 4. What is the voltage drop over resistor 1? Again, it's going to be the total current, but it's not going to be the total resistance like it was in this example. It's going to be the value of resistor 1. So the voltage drop over resistor 1 will then be 0.0225 amps multiplied by 2.5 kilo ohms, or 2,500 ohms. Let's bring the calculator up. 0.0225 multiplied by 2,500. 56.25. Wow. 56.25 volts. Which makes sense. Because it's a larger resistance value, you'd expect a greater voltage drop over this resistor than you would over this resistor. And let's work out what about resistor 2. Well, then it'd be the total current, 0.0225 amps, multiplied by the value of resistor 2, or 1,500 ohms. Let's bring up the calculator again. $33.75 amps. Volts. 33.75 volts. If you add these two values, guys, you'll get 90 volts in total. Finally, calculate the power dissipated by both resistors. So you can see this power equation. There's 3 power equations you can choose from. But it's telling you also that the total power dissipated by this series circuit will be equal to the power dissipated over resistor 1 plus the power dissipated over resistor 2. So we could work out power total, but since this question's asking for both resistors, let's just say that question 6, what's the power over resistance 1, right? We'll use P equals IV because this is the most simple one. We know the total current in this case is going to be 0.0225 amps. V, the voltage drop over resistor 1, not the total voltage, the voltage drop over resistor 1. The power related to this 2.5 kilo ohm resistor is the current flowing through it and the voltage drop it produces. Okay, not the total voltage. So it's going to be what we calculated for resistor 1, 56.25 volts. Oh man, give me a second. 56.25 volts. Put that into the calculator. Or 1.27 to 2 decimal places, 1.27 watts. Over resistor 1. And then what about resistor 2? Well, we're going to have the same current flowing through it because it's a series circuit, so that's not going to change. And we are going to have, what's the voltage drop over resistor 2? 33.75 volts. Put that in the calculator. $33.75. 0.76 watts. And that's how you do the series circuit. Okay, let's have an attempt at a parallel resistive circuit. And let's try and complete these questions here. Pause the video, have an attempt, and then come back and follow through. The first question we gotta finish is, what is the total resistance? We've got to calculate the total resistance here. If you look down here, it's telling us that the total resistance in a parallel circuit is going to be 1 over each resistance value, and then we inverse that. So let's do that. Let's put brackets. 1 over resistor 1. Give me a second. I should write down what we're doing. Resistance total is going to be 1 over resistor 1, 1500 ohms, plus 1 over resistor 2, 3000 ohms, plus 1 over resistor 3, 2500 ohms, all to the power of negative 1. Let's bring up our calculator. Let's open a set of brackets. And let's start us off. 1 over 1500 plus 1 over 3000 plus 1 over 2500 to the power of negative 1. Whoops. Didn't close that bracket correctly. To the power of negative 1. 714.28. To 2 decimal places would be 714.29. 714.29 ohms. So you got to remember that, as discussed in the PowerPoint slides, the total resistance in a parallel circuit, the total resistance, will always be smaller than the smallest resistor in parallel. And the reason why that happens is because you provided the current with additional branches or pathways for it to travel, and that reduces the overall net resistance. Unlike in a series circuit where even if it's a 4 or 5,000 kilo ohm resistor, you've only provided it one pathway to go through. Most of the current here will opt to not go through this 3 kilo ohm resistor. You've given it a choice. It would much rather go through the path with the least resistance. So the majority of current will flow through the smallest resistor. A medium amount will flow through the medium resistor. The least amount will flow through the most resistance. That's why the value of the total resistance is actually smaller than the smallest resistor. Okay, so the next question is draw the series equivalent of this circuit. So let's do that. Right, let's draw the equivalent resistance. So we're going to start off with a supply of 100 volts. And it's going to go through an ammeter. And then that's going to go through this resistance here that we've just worked out. We are not showing protected devices for now. This is 714.29 ohms. And we're going to have a voltage drop over this. The voltage drop in parallel should be whatever the supply voltage is. So this should actually be 100 volts. So that there is the equivalent series circuit to this parallel circuit. This is useful because it lets you calculate what the total current is, which is, funny enough, what the next question is. So let's use this to calculate what this total current should be. So question 3, recall that Ohm's law is V equals IR. So what we can do is to work out the total current, IT. We can say that, that's meant to be an equal sign. We can say that the voltage of the supply divided by the total resistance will give us the total current. So our supply is 100 volts. Our total resistance is 714.29 ohms. Let's bring up the calculator. Let's put a fraction sign. You don't have to, but just so you can, the way I've written it there. 714.29 gives us 0.14 to 2 decimal places, 0.14 amps. 0.14 amps, that's the total. So what's happening is, in this entire circuit here, we have a total of 0.14 amps flowing out of the supply into this ammeter, and then it begins to branch off. Okay, let's do the next question. The next question is asking us, what is the total voltage drop over each resistor? So question 4, and we touched on this already. In a parallel circuit, the voltage drop over each resistor is going to be equal to the supply voltage, because each resistor has a positive, in this case, but it can be an active, and a negative or a neutral path, right? Each resistor gets the supply and can immediately go back to the supply. It's not linked to the next resistor, which is then linked to the next resistor, which is then the only way to get back to the supply. They each can go straight to the supply. So because of that, we can say that the voltage drop over resistor 1 is going to be equal to the voltage drop over resistor 2, which is the same as resistor 3, which is going to be 100 volts. Okay, next question. Calculate the amount of current flowing to each of these resistors. So we've calculated the total current as 0.14, right? 0.14 here. That's the total coming out of that supply. Now we've got to work out how much is going to each of these branches. So question 5. We'll start with resistor 1, the smallest resistor. Ohm's law again tells us that V equals IR. So we're looking for the current going to that branch. Current going to resistor 1 is going to be equal to the voltage over resistor 1 divided by the resistance value of resistor 1. That's going to be 100 volts over 1500 ohms in the calculator. Point 0.067. Amps. Okay, let's work out the current going to resistor 2. It's going to be the voltage over resistor 2, which again is 100 volts. And we have 3000 ohms of resistance. Let's put that in the calculator. We got 100 volts, 3000 ohms, 0.033 amps. And then let's work out current going to resistor 3. I'll do it over here, just to save the space down below. So we're going to have the supply voltage, or the voltage drop over resistor 3, over resistor 3's resistance value, which is 2500 ohms. We are going to have 100, 2500, 0.04 and we are going to say amps. So what's actually happening here is that we have 0.14 amps here. Let me write that. So that's not helping. Maybe if I write it inside here, we have 0.14 amps. That's the total. And then at each branch, we have a certain amount. So a resistor 1, which is the smallest amount of resistance, we have 0.067. Right? At the most resistance, we only have 0.033. And then amps. And then at the medium resistance, we have 0.04. If you add all three of these resistances, you will get 0.14. Just to show you, 0.004 plus 0.033 plus 0.067, 0.14. Okay. So the next question is, what is the power dissipated by each resistor? And hence, we have to provide the power total. So question 6, last question, is what is the total power over resistor 1? So we got power formulas here. And you can use I squared R, V squared R. In the previous video, I used IV. But just to show you that any of these equations will work, we'll use every single one. So for the power over resistor 1, we'll use V squared over R. because they are equivalent equations. It just comes down to what values you're given. So the voltage squared is going to be 100 squared. Right, that's the voltage over resistor 1. It's the same for each resistor actually. And the resistance is 1500 ohms. That's volts, by the way. Put that in the calculator. We have 100 squared over 1500. 6.67 watts. What about the power of resistor 2? We use I squared R, Joule's law. I squared in this case would be 0.033 amps, 0.033 amps, which we worked out here. Or should I say here as well? All squared times the resistance value for resistor 2, 3000 ohms. Calculator time. Open bracket. 0.033 squared multiplied by 3000 ohms. 3.27 to do decimal places. Watts. What about the power over resistor 3? And for this one, we'll just use I squared. IV. In this case, the amount of current is 0.040 amps times 100 volts. Now, what you could just do is immediately move the decimal place back, but just to show you in the calculator. Four. So the total power and what I mean by you could have just moved it, I'm going to do a video and a unit on maths for electricians and electrical apprentices, is that 100 is 10 to the 2, right? So 10 to the 2 just means that you're going to move this decimal place back 2 places, and that would give you 4.0 amps. But we'll deal with that in another video. So 4 watts. So the total power should be 4 watts plus 3.27 watts plus 6.67 watts. 4 plus 3.27 plus 6.67, 13.94. 13.94 watts. That's the total power dissipated. And you can verify that by just doing this. So we have 714, right? So what would be the total power here? It'd be 0.14 amps multiplied by 714.29 ohms. Sorry, this would be squared, I should say. Squared. And let's bring up the calculator just to verify what we've done. So we got 0.14 We're going to square that. Multiplied by 714.29 ohms, 14.00 watts. If we round this to the nearest whole number, it'd also be 14.